Welcome to the next session on Module 5, that is Potentiometry. Potentiometry is an instrumental technique in which the EMF of the solution is measured so as to determine the concentration of ionic species present in the solution. The relationship between electrode potential and metal ion concentration is given by Nernst equation as E is equal to E0 plus 0.0591 by N log concentration of Mn plus. So here the potential of the electrode E, it depends upon the concentration of metal ions to which it is reversible. Now coming to the instrumentation part, a potentiometer, it consists of a reference electrode which has a fixed potential and it is independent on the concentration of the analyte solution. And here the reference electrode used, it is a calomel electrode, and an indicator electrode whose potential depends upon the concentration of ions in the analyte solution, and a device for measuring the potential. A known volume of analyte, it will be taken in the beaker, and its potential, it is determined by connecting to the potentiometer. Now the titrant, it will be added from the burette in increments of 0.5 ml. So after adding 0.5 ml, the solution, it will be mixed thoroughly, and again the potentiometer reading will be recorded. Near the equivalence point, there will be a sharp increase in the potential, and the endpoint is determined by plotting change in potential with change in volume, that is delta E by delta V against the volume of the titrant. Now coming to applications, it is used in redox titrations, that is in the reaction between ferrous ammonium sulfate and potassium dichromate. It is used in acid-base titration. For example, titration of HCl against sodium hydroxide. It's used in precipitation titrations. For example, silver nitrate against potassium chloride, whereby silver chloride, it gets precipitated. Then in colored solutions, they can also be titrated by using potentiometric method. Now coming to the laboratory part, estimation of ferrous ammonium sulfate potentiometrically using standard potassium dichromate solution. So here in the beaker, we'll take 25 ml of ferrous ammonium sulfate that will be provided to you. To that you will be adding 10 ml of dilute sulfuric acid, because here we are taking in the burette potassium dichromate. Potassium dichromate, it is a strong oxidizing agent only in presence of acid. So for that purpose, we are making use of 10 ml of dilute sulfuric acid. It will be added to 25 ml of FAS taken in the beaker. Now the reaction that is taking place is chromium, here it is in the +6 oxidation state. It will be reduced to chromium in the +3 oxidation state, whereby this potassium dichromate, it will oxidize the iron in the Fe2 plus state to Fe3 plus state. And Nernst equation for this reaction, it is given by E is equal to E0 plus 2.303 RT by NF log concentration of iron in +3 oxidation state divided by concentration of iron in +2 oxidation state. That means oxidized state by reduced state. Now potassium dichromate, it will be added in increments of 0.5 ml. So every time after addition of 0.5 ml of potassium dichromate, the potential, it will be noted. So you will be noting the potential after addition of 0.5 ml of potassium dichromate every time. And the change in volume, it will be 0.5 ml, because every time we will be adding only 0.5 ml of potassium dichromate. Now delta E value, it will be the present reading minus previous reading. It will give you the delta V value for any particular ml. Say for example, for after 1.5 ml of addition, if you want to determine the delta E value, it will be this value minus previous value. That will give you the delta E value for 1.5 ml. So like that, the change in potential for each addition you have to find out, after which you have to find out delta E by delta V, and a graph is plotted with delta E by delta V against volume of potassium dichromate. And from the graph you can find the equivalence point. That is, you can see that there is a sharp increase in delta E by delta V value, and the volume of K2Cr2O7 corresponding to this peak value. It will be the volume of K2Cr2O7 that is required for the equivalence point. Now, from the graph, volume of K2Cr2O7 at the equivalence point, it can be obtained. Now, normality of K2Cr2O7 it is provided to you, that is 0.5 normal, because we are making use of a standard potassium dichromate solution, that is whose normality is known to us. Then volume of FAS taken in the beaker, it is 25 ml of FAS that has been provided to you. Now, normality of FAS, it can be calculated using the equation N1V1 by V2. N1 it is 0.5, V1 it is obtained from the graph, and V2 it is 25 ml. So weight of FAS per liter, it will be N2 into equivalent weight of FAS. Equivalent weight of FAS, it is 392. So you will get it as so much gram per liter. So this will be the weight of FAS that is present per liter of the solution that has been provided to you. So this is how we determine the amount of substance present in a solution potentiometrically. Thank you.